So midterm exam 1 problems. So in problem 1, we have the vectors u equal to 1, 1, 7, and v equal to 2, 3, 5. So if you add them, you add coordinates, you get 3, 4, 12, and 3, 4, 12. And so the length of this vector is the square root of the sum of the squares of the coordinates, 3 squared plus 4 squared plus 12 squared. That's the square root of 9 plus 16 plus 144, which is square root of 169, which is 13. If you have questions as I go through the exam, just unmute yourself and ask. The dot product is the sum of the products of coordinates, 1 times 2, 1 times 3, 7 times 5. That's 5 plus 35. That looks like 40. And if you have, and what is the dot product of two vectors? It's always the length of the vector u, the length of the vector v, cosine of the angle between them. So the cosine is the dot product divided by the product of the lengths. So the dot product is 40. The length of u, if you take the sum of the squares of the coordinates, you get 51. If you take the sum of the squares of the coordinates of v, you get 25, and 9 is 34, is 39. Let me see if that's right. 49, 50, 51. And 4 and 9 is 13, and 25 is 38. So that's what it is. Can't do anything better than that. And if you want to project the vector u onto v, this is the projection. The projection of the vector u onto v, it's a vector in the same direction as v. It's a certain scalar multiple of v. It's the dot product of u and v divided by the length of v squared times v. So the dot product of u and v is 40. The length of the vector v is square root of 38. So if you square that, you get 38 times the vector v, which is 20 over 19, times the vector 235. Any questions about that? This is A, B, C, and D. In problem 2, we have the vector with coordinates 1, 0, 3, and 0, 2, minus 3. And the cross product, you compute this 3 by 3 determinant, minus 1, 0, 3, 0, minus 2, 3. When you compute this, let's see, what do you get? You get this determinant, minus 6, 6i, minus this determinant times j, that's minus 3, so minus 3 is plus 3, plus this determinant plus 2k. So that's the cross product of the two vectors. And if you have these two vectors, u and v, the length of u cross v is we can define this in two ways. First of all, it's the area of the parallelogram generated by the two vectors u and v. If these are adjacent vectors and you construct their parallelogram, the magnitude of the cross product, that vector, is the area of that parallelogram. So this is the cross product. So this is the square root of 6 squared plus 3 squared plus 2 squared, which is 36 plus 9 is 45 plus 4 is 49. So this has area 7. But u cross v is also equal to, well, it's not, let's do that. And u cross v is orthogonal to both u and v. So a unit vector, let's call it u, orthogonal to u and v, well, that's not called u, it's called n, let's say. It's this vector divided by its length. So that's the vector, and the length is a seventh. It's 1/7 times the vector 6, 3, 2. So this is a unit vector perpendicular to minus 1, 0, 3, and 0, minus 2, 3, as you can check directly. Any questions about that? In problem 3, we have a vector valued function r of t, which is 4ti plus cosine 3tj minus sine of 3tk. You get the derivative just by differentiating term by term. 4i minus 3 sine 3tj minus 4 cosine 3tk. The indefinite integral, you get by just integrating term by term. The integral of 4t is 2t squared. The integral of cosine 3t is 1/3 sine 3t. The integral of minus sine 3t is 1/3 cosine of 3t plus an arbitrary constant. That's the indefinite integral. And the definite integral from minus pi over 3 to pi over 3 of r of t dt, you get by taking this indefinite integral and evaluating that from t equal minus pi over 3 to plus pi over 3. 2t squared at pi over 3 and minus pi over 3 are the same. First coordinate is 0. 3t is pi or minus pi. Psi of them is, but each of them is 0, so this is 0. Cosine of pi and cosine of minus pi are both minus 1. So this integral is just 0, the 0 vector. That's the answer. Any questions about that? Okay. Problem 4, you have the point in rectangular coordinates 1, 1. And if you want to convert that to polar coordinates, The distance from the origin to the vector is square root of 2. And this angle is pi over 4. So 1, 1 in rectangular coordinates is root 2 pi over 4 in polar coordinates. If you have the point 2 pi over 6 in polar coordinates, so if this angle is pi over 6, and this distance is 2, this point in polar coordinates is 2 pi over 6. And in rectangular coordinates, what is it? Well, this is 2 times the cosine of pi over 6, and this is 2 times the sine of pi over 6. In a pi over 6 right triangle, this is half the hypotenuse. This is 1, and this is root 3 times 1, root 3. So this, when you change this to rectangular coordinates, you get square root of 3, 1. And if you take the point 1, 1, 1, sorry, if you take the point 2, 2, 2 in cylindrical coordinates, here's the point 2, 2, 0 in the plane, and you go up 2 units. So this is the point 2, 2, 1, 2, 2, 2. So here you have this point in rectangular coordinates, and when you change it to cylindrical coordinates, the third coordinate is just the same as the z coordinate. It's the height above the x-axis. That's 2. And to find the first 2 coordinates, you look at the projection of this point in the xy plane, that's 2, 2, 0, and you want to find the polar coordinates of this point. This is r, and this is my theta. So if you just sort of write this like in the xy plane, it's like you're looking at the point with coordinates 2, 2. What are the polar coordinates of that point? This is pi over 4. This is 2 root 2. All right, this is 2 root 2. This is pi over 4. So this is 2 root 2 pi over 4, 2. Those are the cylindrical coordinates. Any questions about that? Problem 5, we have in space, we have the point 5 minus 2, 4, and we want to find the line going in the direction of the vector v equal to 1, 2, and 3. So we want to find the line through this point in this direction. So this has coordinates. X of t will be 5 plus t. Y of t is minus 2 plus 2t. Z of t is 4 plus 3t. So these are the parametric equations of the line through this point in the direction of the vector 1, 2, 3. And if you want to find, for that same point, 5 minus 2, 4, the plane going through this point with a normal vector n equal to 1, 1, minus 1. So a point lies in the plane, a point x, y, z lies in the plane. If the vector from the point 5 minus 2, 4 to x, y, z is perpendicular to n. So that means, so this vector has coordinates x minus 5, y minus 2 is y plus 2, and z minus 4. And that has to be perpendicular to the vector 1, 1, minus 1. So 1 times this plus 1 times this plus minus 1 times this equals 0. That's x plus y minus z. Here I have minus 5 plus 2 plus 4. Minus 5 plus 6 is 1. It's minus 1. Let's see. No, I don't think that's right, so let me just double check. X minus 5, y plus 2, minus z minus 4. This is 2 plus 4 is 6, minus 5 is 1. So x plus y minus z is 1. So 5 minus 2 is 3, minus 4 is minus 1. So that's okay. That's the equation of the thing. Problem 6, you have a particle whose position at time t is 1 minus t squared, 3 plus 2t cubed, 7t. So this is just a quick exercise to make sure you know what velocity and speed and acceleration are. The velocity is the derivative of the position. You differentiate coordinate-wise. The derivative of 1 minus t squared is minus 2t. The derivative of 3 plus t cubed is 2 times 3 is 6t squared, and the derivative of 7t is 7. And the acceleration is the derivative of the velocity, so you just differentiate this, you get minus 2, 12t0. And the speed is just the length of the velocity. So that's the square root of minus 2t squared plus 6t squared plus 7 squared. So that's the square root of 36t to the 4th plus 4t squared plus 49. That's the speed. In problem 7, we have to find the time of flight, range, and maximum height of a trajectory moving under no force except gravity, where a particle has starting position x naught, y naught equals 0, 0. And the initial velocity, u0, v0, is 4, 48. The units are feet per second, which means the acceleration is 0 minus g, which is 0 minus 32. That's the acceleration. So this is initial velocity. This is acceleration. This is initial position. So if the acceleration is 0 minus 32, then the velocity at time t is the integral. It's going to be, the integral of 0 is a constant. The integral of minus 32 is minus 32t plus a constant. V at time 0 is c1, c2, which has to be 448, which means that the velocity is given by c1 is 4 minus 32t plus 48. That's the velocity at time t. And the position, r of t, is the integral of the velocity, So you integrate 4, you get 4t plus some constant. And you integrate minus 32t plus 48, you get minus 16t squared plus 48t plus some constant. And r at time 0 is C1 prime, C2 prime, which is 0, 0. That's the starting point. So these constants are 0. So the position at time t is given by 4t minus 16t squared plus 48t. So what is the range? So this particle, it shoots up at time 0 and it goes through the air and it hits the ground. And at t equals 0, it's at 0. And what does it mean to hit the ground? So particle is at ground level when its height, y of t, is minus 16t squared plus 48t is 0. Minus 16t squared plus 48t is equal to minus 16t times t minus 3. And this equals 0 at t equals 0 and t equals 3. T equals 0 is when it's launched. It's at ground level. The height is 0. And at t equals 3, it hits the ground. So the time of flight is 3 seconds. And where does it hit the ground? The range is the value of the x coordinate at t equals 3. That's 4 times 3, or 12. So this particle only goes 12 feet. And what is its height what is its maximum height in the flight? So you look at y of t. Y of t is minus 16t squared plus 48t. This has a maximum, the maximum height, at y prime of t equals 0. Y prime of t is minus 32t plus 48 equals 0 when t equals 48 over 32, or 3/2 seconds. And y at time 3/2 is what? Minus 16, 3/2 squared, plus 48 times 3/2. This is 9/4. This is minus 36 plus 72 is 36 feet high. So at its maximum, it's 32 feet. It's 36 feet above the ground. And what is the trajectory? So we have at any time t, x is equal to 4t, and y is equal to minus 16t squared plus 48t. 16t squared is 4t squared, and 48t is 12 times 4t. So if you want to y in terms of x, y is equal to minus x squared plus 12x. And that's the parabola, the graph. It's a parabola that looks like that. 0, 3, and a 3/2. This is its maximum height. 3/2, comma 36. But in the xy plane, this is what the trajectory looks like. Sorry, this is 12. Right? It starts at time 0, goes up, comes down, hits the ground at 12 feet away, 3 seconds later. That's the trajectory. Any questions about that? And the last problem, problem 8, on arc length. If we have, so the formula for arc length, let's say L, the integral arc length of a curve from A to B is the square root of the sum of the squares of the derivatives. If it's in the plane, if there are only two derivatives, it's x prime squared plus y prime squared. And if it's 3 space, there's also a z prime squared. So in part A, we're in the plane. R of t is 3t squared minus 1, 4t squared plus 5. So L is the integral, t goes from 0 to 1, of the square root of the sum of the squares, the derivatives. The derivative of 3t squared minus 1 is 6t, so we're squaring that. The derivative of 4t squared plus 5 is 8t, so we're squaring that dt. This is 36 plus 60. This is 100t squared. So this is the integral from 0 to 1 of 10t dt, which is 5t squared evaluated from 0 to 1, which is 5. So the arc length of this curve in the xy plane is 5. If we take the curve in the xyz plane in space, so here r of t is 3t minus 1, 4t plus 5t. The length of arc is the integral from 0 to 1, square root of the derivative squared. Derivative of 3t minus 1 is 3. Derivative of 4t plus 5 is 4. Derivative of t is 1 dt. This is 9 and 16, and 1, this is square root of 26. The integral from 0 to 1 of 1 dt, which is just 1. So the length of this curve is the square root of 26. Okay. Any questions about that? All right. That was the little exam. And now we go to chapter 15, which is on functions of several variables. So in the previous chapter on vector valued functions, that's a function like r of t, which goes from the line into space. So you have some interval maybe from A to B. And you have this function r of t, and it traces out some curve in space, two-dimensional or three-dimensional. So this is in the previous chapter, we had vector valued functions. So you went from one dimension into 2 or 3 dimensions. Functions of several variables is the opposite. So you might have a function of 2 variables, f of x, y. So in some region of space, your function maps this into just the line. So f of x, y is a number, or a function of 3 variables. You have some region of space, and again, you have this function, f of x, y, z now, which gives you a number. Okay. So for example, you might have f of x, y is x squared plus y squared. So if you take the vector 2, 3, that has the value 2 squared plus 3 squared, or 4 plus 9, or 13. Okay. Or f of x, y, z equal x, y, z plus 2 to the x minus y, z minus y squared. I mean, that's a function of x, y, and z. Like f of 1, 2, 3 is 1 times 2 times 3 plus 2 to the first power minus y, that's 2 squared. That's 6 plus 2 minus 4 is 4. Right? So in a function of several variables, and for us, it's only going to be 2 or 3 variables, for every vector, you assign a number. For a vector valued function, to every number you assign a vector. This is in the opposite direction. To every vector, you assign a number. So here's an example. G of x, y equals square root of 4 minus x squared minus y squared. So this is a function of 2 variables, but it's not always defined. Like g of 5, 2 would be the square root of 4 minus 5 squared minus 2 squared. That's 4 minus, that's square root of minus 25. This is undefined because we can't take in real numbers the square root of a number that's negative. So for any function, the domain of this function, in this case, the domain of g of x, y, is the set of all vectors x, y in the plane for which g of x, y is defined. So if g of x, y is the square root of 4 minus x squared minus y squared, this is only defined where 4 minus x squared minus y squared, you can't take the square root of a negative number, so it's defined where this is greater than or equal to 0, which is the same as x squared plus y squared less than or equal to 4, or 2 squared. And what is this in the plane? X squared plus y squared equals 4 is the circle, and x squared plus y squared less than or equal to 4 is the disk of radius 2 and center at the origin, right? So this function of 2 variables is only defined where x and y lie on or inside the circle of radius 2. So a function of several variables is, just as the name says, a function of several variables. Now, we like to graph functions in calculus 1 and 2, like in calculus 1 and 2, you might have a function of 1 variable and it has a graph. Say this is the graph maybe for x between a and b. So here's a and here's b, and the graph is the set of all points x comma f of x, where x is between a and b. So you get some curve. So the curve is the graph of a function of 1 variable. Suppose I write z equals f of xy is a function of two variables. And suppose we want to look at this maybe for x between a and b and y between c and d. So if this is a, b, c, d, the set of points where x is between a and b and y is between c and d are the points in this rectangle. And for any point xy in this rectangle, we assign a number z equal f of xy. And one way to think of the graph of a function of two variables is the following. Suppose we have three-dimensional space. Here's the xy plane. So if this is, say, a and b on the x-axis and c and d on the y-axis, the points with x between a and b are in this strip. The points where y is between c and d are in this strip. So with this perspective, this is the same rectangle. And for every point xy in this rectangle, I look at the point above it with coordinates xy, f of xy. And as xy varies through this rectangle, these points will vary in space, and the graph of a function of two variables is a surface in three-dimensional space. So just as the graph of a function of one variable was a curve, and curve is the graph of a function of one variable in the two-dimensional space, the graph of a function of two variables is a surface in three-dimensional space. Right? And in general, these are hard to draw by hand. So there's special cases where you can do it, but in general, it's almost impossible. It's not almost impossible. It is impossible in general to figure out what the graph of a function of two variables looks like. Now, if you know Maple, Maple can do three-dimensional plots, and you can sketch things in Maple and get some idea of what's going on. And if you don't have Maple and are interested in it, you can get it for free as a CUNY student. It's expensive to buy, but if you can get it for free, it's software that CUNY distributes to everyone for free. And I'm happy to show you how to use it if you get it. Okay. There is a kind of, so in Calculus 1, how to tell if a curve is the graph of a function y equals f of x. Like that's the graph of a function. This is a graph. But you can think of it as, say, from A to B, or any point x, the height is the value of the function at x. If you had a curve that looked like this is not a graph. Is not a graph. Because even though this is like between numbers A and B, if you take a point X, there are two different points above X, and you want one of them to be f of X. You can't have two of them equal to f of X, right? This is not, there's no function of X which takes on two different values at X. So this is not a graph. So we could ask the same thing about a surface. How to tell if a surface in R3, it's three-dimensional space, it's the graph of a function z equals f of xy. Well, it's exactly the same way. If you have a surface over some region in the xy plane, this is your surface. And for any point xy, if you draw the vertical line, it hits the surface in just one point, z, then you can say that z is the value of the function f at xy. So, but if you have, let's say you had a sphere. This is a sphere in space. If you take a point, let's say on the surface of the sphere, and you drop the perpendicular to the xy plane, there are 2 points on the sphere above that point. So if you have this point xy, what is f of xy? It can't be two different numbers. The function has to be single value for any xy. There's just one z equal f of xy. So in both cases, for curves and surfaces, a graph must pass what you might call the vertical line test. That is, any vertical line hits the surface of the curve in at most one point. Right? And any object, any curve in the plane which passes the vertical line test is the graph of a function. And any surface in space that passes the vertical line test also is the graph of a function. But as I say, it's hard to figure out what these things look like. But there are some special cases where, and it's important to know them because it gives you examples to learn your subject from. Like, suppose you have the function f of xy equal 2x plus 3y minus 12. So, graph this function. So if you have z equal 2x plus 3y minus 12, that's the same as 2x plus 3y minus z equals 12. And this is a plane. With normal vector n given by the coordinates of x, y, and z, 2, 3, minus 1. And passing through, we'll just find any point on the plane. For example, if x is 6 and y and z are 0, this point satisfies this equation. And this is the equation of the plane passing through this point with normal vector 2, 3, minus 1. So, and in general, f of xy equal ax plus by plus d is the equation of a plane in space. So if you have your f of xy as a function, which is something times x plus something times y plus a number, that's always the equation of a plane. Suppose you have g of xy equals x squared plus y squared. So what does the graph of that look like? So g of 0, 0 is 0 squared plus 0 squared is 0. So the origin of the three-dimensional space lies on this. What are the points at height 1 above the xy plane? So if g of xy is equal to 1, that means x squared plus y squared equals 1. So in the xy plane, if you take the circle of radius 1, those points get moved up height 1. Okay. What are the points of height 4? They're the points where x squared plus y squared equals 4, or 2 squared. Those are the points that are on the circle of radius 2. And they're up there. And in general, if you try to figure out the graph of the function x squared plus y squared plus z squared, you get a function which looks like this. It's like you take the parabola and you rotate it. So this is called a paraboloid. In fact, this method of trying to get some idea of what the surface or the graph of a function of two variables looks like is called the method of level curves. So let's stick with this example for another couple of minutes. So I'm looking at the function g of xy equal x squared plus y squared. And the graph of this function, like if you took x equals 0, this would just be y squared equals z. It's just a parabola. And the whole surface looks like this parabola rotated around the origin. It's a paraboloid. So the level curve f of xy equals z naught is all points in the xy plane such that this equation is satisfied. So what is the level curve, or let's say I'm using g for the function. What is the level curve g of xy equal 1 for the function x squared plus y squared? That's all points where x squared plus y squared equals 1. It's the circle of radius 1. So the circle of radius 1 in the xy plane these are all the points where f of xy equals 1. What is the level curve g of xy equal 4? So all points where x squared plus y squared equals 4. That's the circle of radius 2. So this is z equal 1. This is z equal 4. What's the level curve g of xy equals 2? It's all points where x squared plus y squared equals 2, which is the square root of 2 squared. That's the circle of radius square root of 2. This is the point 1. This is the point root 2. So the level curves of this function are circles in the xy plane. If you are hiking, for example, these are just like typographical maps which show you the height above sea level at a point along in the area where you're going to go hiking. And if these level curves are very densely packed, that means the surface is very steep. It's going up quickly. If the level curves are far apart, then the increase in height in the surface is very low. It's very gradual. If you draw level curves for z naught equals 0, 1, 2, 3, and so forth, if they look like this is kind of slow growth. As you go from here to here, the function is getting bigger, but slowly. If your level curves look like this, it means as you go a small distance, you're going up a lot. So this is fast growth. So looking at how densely packed or far apart separated are your level curves tells you something about how quickly your function is increasing or decreasing. Now, I'm going to encourage you to spend a lot of time looking at section 15.1 and studying the pictures. Just the more you do that, the better. This is really a pencil and paper subject right now in level curves. You have to look at examples and try and draw pictures as well as you can. Now, suppose we have a function z equals f of xy. So the graph is some surface in space. Let's compare that with y equals f of x, a function of one variable. And the graph is a curve in the plane. And you might want to know how quickly, like the function y equal f of x is changing. So in a region like this, where it's going up quickly, the measure of how quickly this curve is changing, which is the slope of the tangent line to the curve, here the derivative would be big, going up rapidly. Here, where the function is increasing very slowly, you expect the derivative to be slow, to be small. But what about with the surface? Now, surfaces are really complicated. I mean, like how the surface is changing as you go, like here, as you go from x to x plus delta x, there's a big increase in the function. What about if you look at a point xy? If you vary it a little bit, you want to know how much does your function, the value of the function change. But this is a little more complicated because there's only one way to change x. It can get either bigger or smaller, x plus something or x minus something. But to change the point xy, so if this is xy, you could go a certain amount in the x direction. This would be, let's say, x plus hy. Or you could go a certain amount in the y direction from xy to xy plus h. And the function can change as you go in one direction at a different rate from what it changes when you go in the other direction. So as a first step in understanding how rapidly a function changes at a point, you can ask how much does it change as you go in one direction from the point. Let's say you fix y and change x. So you have a function z equal f of xy and fix y equal y naught. So it gives some, so you actually have z is f of x y naught is fixed. So now this becomes a function of x. And you can differentiate this with respect to x. With respect to x. Let's take an example. Suppose I have f of xy equals x squared plus y squared. And suppose I let y equal 3. So my function f of xy is f of x3, which is x squared plus 3 squared, or x squared plus 9. So in the xy plane, if you fix y equal 3 and you just let x vary, you're moving along a line in the xy plane. That's a function of x. And the derivative with respect to x, we use curly t's instead of t's. Partial of f, this means partial derivative, because you're differentiating with respect to only part of the variables, x. The derivative, the partial derivative of f with respect to x is just what you get when you differentiate this function with respect to x, which is 2x. And that gives you an idea of how rapidly or how slowly your function is varying as you change the x value. Or in this function, f of xy equal x squared plus y squared, you could fix x. Maybe that x equal 5. So f of xy is really f of 5 comma y. That's 5 squared plus y squared. The f of 5y is 25 plus y squared. And if you differentiate this with respect to x, you get your other partial derivative. The partial derivative of f with respect to y is 2y. So I guess all I want to do today is throw out these ideas so you get to see them and think about them a little bit, and you'll have some homework to do with them. But whenever you have a function of 2 or 3 variables, you can look at the partial derivatives. And just by analogy with the derivative of a function in Calc 1, remember if you have a function y equals f of x, f prime of x, or df dx, is the limit as h goes to 0 of f of x plus h minus f of x over h. If that limit exists, It's called the derivative. If you have z as a function of two variables, f of x, y, the partial derivative with respect to x, so you fix y doesn't change. This is the limit as h goes to 0 of f of x plus h comma y minus f of x y over h. And the partial of f with respect to z is the limit as h goes to 0 of f of x y plus h minus f of y over h. Sorry, partial of f with respect to y. So for example, if you have f of x, y is this polynomial 3x to the fourth y minus 2xy plus 5xy cubed. If you want to find the partial of f with respect to x, you think of y as a constant, you fix y, and you differentiate with respect to x. The derivative of 3x to the fourth is 12x cubed times y. The derivative of 2x is 2 times y. The derivative of 5x is 5. That's 5y cubed. So for this function, this is the partial of f with respect to x. And the partial of f with respect to y, if you fix x, this is 3x to the fourth times y. The derivative of y with respect to y is 1. So this is 3x to the fourth. Derivative of y with respect to y is 1, so minus 2xy has a derivative with respect to y of minus 2x. The derivative of 5xy cubed with respect to y is 5x times the derivative of y cubed, which is 3y squared. So this is 15xy squared. Right. Any questions about this? Okay. So I think I'm going to stop at this point because the object for today was just to go over the exam and begin to introduce functions of several variables, which we study for the rest of the semester. And it's the calculus of functions of several variables that will concern us a lot. So you should really try, I think I've given some homework. If not, I'll make sure it's posted by the end of the day. So you have some problems on trying to graph surfaces by hand, which is a useful exercise. And if you know Maple, Maple has a 3D plot command, which is unbelievably useful in this context. Okay. Any questions about this? If not, then I think we will stop and enjoy what seems to be a lovely day. So see you all Monday morning at 11. Okay, bye all.
Have a good one, Professor. See you Monday.
Thank you. Bye-bye.
Have a good day.
Thank you.